Thank you very much, Joe and John, for inviting me to speak here. This is a new group for me and a very enjoyable one. A lot of old friends, a lot of new acquaintances. It's also a great chance for me to proselytize about wading birds. You thought waterfowl were cool. I'm going to try and turn you. These are really fantastic birds. I'm going to be talking about detecting ecological surprise. What is ecological surprise? Ecological surprise is, of course, something you didn't expect. And it's usually something you didn't expect that happened because of something that we were doing. So when you get a large ecosystem and you try to model any aspect of it, you can usually do that. But modeling all aspects of it are very hard. And in fact, mathematically, it becomes chaos at some point, literally mathematical chaos. So at some level, no matter what your intentions are for any ecosystem, things are going to turn out not quite the way you thought they would. Not having a monitoring system out there is therefore crazy. You've got to have a monitoring system. You've got to be willing to admit that something's going on that you didn't predict right up front if you're going to be able to react to it quickly enough to make a difference. So wetlands in general react fast to almost anything we do. Wetlands are places that are now multiple use. What was once a place just for hunting or just for recreation now has many, many things going on in it and is responsive to lots of different needs. Water storage, recreation. It's also got now things like exotic species that we didn't have before, and climate change, and sea level rise, and lots of things that we find very, very hard to predict. So, all the more reason to be expecting ecological surprise and trying to design monitoring systems for it. I'm going to be talking today about a particular monitoring program that's been going on for maybe not continuously, but close to a century. One that has a really rich heritage and lots of information that has been able to inform in the end the largest ecological restoration project in the world. Along the way, I'll talk first about indicators in general and monitoring in general, then about the birds and their ecological attributes and needs, then about some of the things that they've shown, some of the surprises that they've shown us on very large scales. Okay, everybody understands canary in a coal mine and what an indicator is. That's very obvious, and I don't need to repeat any definitions for you. I think we run into some trouble sometimes unless we obey some rules about indicators. An indicator should have a known relationship with ecological parameters. Otherwise, what is it really indicating? Sometimes we begin to study things and call them indicators before we really understand what it is that they're reflecting. They should be a lot cheaper than monitoring the whole system. Caddisfly larvae really are sensitive to oxygen. So all you have to do is walk in the stream, look for the caddisfly larvae. If they're not there, you know that the oxygen's low, right? That's a lot cheaper than wandering up and down the stream with an oxygen meter. I would not trust a doctor if he told me that my blood oxygen or any other parameter about me reflected my health. There's lots of things that they look at. And so the same is true of ecosystems. You need lots of indicators. There are no one group or one animal that's going to tell you everything about it. These things look very, very straightforward here. They're very easy to forget when you're designing these. Monitoring, many people call themselves monitoring indicators. In some cases, all they're doing is monitoring species. Monitoring species is okay. We monitor lots of things. Endangered species, ducks and geese. We monitor lots of things that are for the sake of that animal or that group themselves. We want to know something about that species because we care about it, and that's fine. But unless you do understand the ecological relationships, then you're not really monitoring an indicator. Indicator monitoring may be very broad and diffuse, like the North American Breeding Bird Survey, which has lots and lots of species out there being monitored over a very large geographic range. We know a lot about those species, but we don't really know exactly what the stressors are that we're looking for a response from. We're casting a broad net. We're casting a net that will catch almost anything that comes down the pike. The other end of the spectrum, though, is monitoring a species in which you really do understand the biological relationships. you're looking for a specific effect or lack thereof in management or in some kind of stressor, and you're actually doing hypothesis testing with it. And that's sort of the other end, very, very specific monitoring. I'll talk about some aspects of each one of these. On to the Everglades. This is a picture taken in 1942 by Alexander Sprunt, who somehow talked the Navy into flying one of their float planes over the Broad River colony. And up here you can see the Broad River here with mangroves all around it. And then that's all the dark stuff. And then the white stuff out here is marl prairies and sawgrass. And all this white stuff that looks sort of like snow, that's white ibises nesting. Sprunt thought there were over 60,000 pairs nesting in this colony. My guess, it was a pretty wild underestimate. But he really didn't have a lot of good counting mechanisms. He only had one day in the plane and so forth. Sprunt went back, and so these big colonies were really characteristic of the Everglades. In many cases, we did not have any kind of an aerial photograph. This is the first one that I know about. So we do know that people were finding them 1880s, early 1900s, 1930s. They were characteristic of this system in a largely pre-drainage state. So there's something about the Everglades that can create this enormous wildlife spectacle. Now, Sprunt actually went into this colony, and this is what he wrote about it. This is an experienced ornithologist, okay? He wrote that it was impossible to describe it as if humanity had ceased to exist, as if the world was peopled entirely by birds which might eject us at any point. Now, I don't know when was the last time you had that kind of experience with birds, but these were very special places, and they were inspiring. And so the first reason why Sprunt was in there was because Audubon had been monitoring these birds for a long time because of the plume hunting era. But that was long since over by 1942. What was he still doing there? Well, we didn't have Everglades National Park. They were actually worried about development at that time, and they were worried about these specific birds. But the reason that they were still funded was because these birds inspired beauty and aesthetic sense and this really remarkable phenomenology. So that's why we started monitoring them, not with any specific ideas in mind about what we were going to find or what the ecological relationships might be. Very quickly, I'll just talk about the foraging ecology of these birds and especially how they get lunch, because that turns out to be, the foraging ecology is really critical to just about everything else I'm going to say. They all have long legs. They all have long bills. They all pick things out of the water. But beyond that, the similarities sort of stop. The wood stork down here is holding its mouth open, its bill open, and waving it very slowly through the water, hoping that something will run into the bill and it'll snap shut. And they capture things just as efficiently with blinders on their eyes as they do with their eyes open. So they're not using their visuals at all. You can imagine that this technique, and the same with the spoonbills, also is tactile foraging. It only works when you've got a lot of prey in that bucket of water. So think about going into a completely dark bathroom where there is a bathtub that has water in it, and it's got some number of fish in it, and you're supposed to wave your hand around and catch fish. That's exactly what the wood stork and the spoonbill, and to some extent ibises, are doing. You can also imagine that if there are a lot of fish in there, it's going to be a lot easier than if there's a few. And if the water is deep, it's going to be a lot harder than if it's shallow. So essentially, you have wading bird foraging ecology right there in the palm of your hand if you go in and do that in a bathroom. Great egrets, on the other hand, are not foraging tactilely at all. They're foraging by sight. And their big advantage is that they're stalking slowly, sneaking up on things, and then they have a harpoon-like bill and a snake-like neck, which propels that bill forward at incredible speeds. Snowy egrets are doing something, they're also sight foragers, but they're also doing something a little bit different. They're trying to do everything by surprise, running around fast, landing, stabbing, and just moving really quickly from place to place. So this gives you some appreciation of the fact that a wading bird, there is no such thing as a wading bird. There are lots of species. They're all doing different things. And they may actually react somewhat differently to different water levels and different prey densities. But they're all really dependent upon these conditions. The conditions under which you're going to get a lot of prey available is when prey are dense, when the water level is really shallow or being drawn down in some fashion. Low oxygen can force fish to the surface of the water. And of course, anytime you have lots of vegetation, it means the fish can hide. So, that sort of degrades things. Also, if you have lots of densely flocking birds, there's a confusion effect created by them. A bird might miss one fish here, but it runs into the bill of another bird. So these are the conditions that the birds really like. And the thing to remember is that these conditions are ephemeral. If you have that shallow, low oxygen pond, it's not going to last forever. The birds are going to deplete it. The fish are going to die. The birds are going to have a landscape that they can move across throughout a long period of time if they're going to be able to breed and get food every day. Okay, wading bird nesting is definitely related to food. It's related to food in part because we can't find anything else that it's related to. These guys don't seem to be responsive to disease or predation or human disturbance very much or lack of nesting substrate. So at least in South Florida, this is not what's limiting them. Whenever you get interruptions in the food supply, the birds abandon. Whenever you have anything that increases the food supply, the birds breed like crazy. So it's almost like a sort of feedlot. I've always joked that if somebody gave me a couple of military transports full of fish and allowed me to fly over the Everglades and dump them, I could make breeding happen. There's no question. It's really all about the food. Okay, the Everglades marsh is distinctive in that it has very low nutrient status. I think Steve said cleaner than rain. That's about right. It has it's almost sterile. And so a central question about the Everglades has always been, how does this extremely sterile, very oligotrophic place create these huge wildlife spectacles? How does it happen? By what process? So one of the ways that we know it happens is because we have a wet-dry cycle. And this is a hydrograph over a period of about 20 years, in which we have a typical wet period of water rising and then falling somewhere between November and May. So wet, dry, wet, dry, wet, dry, wet, dry, wet, dry. That pulse is always going on in South Florida. Whenever it's drying, you're going to get exposure of these fishes and crayfishes and things to the birds. But the really crucial thing to remember is that every year here is not like every other year. There's enormous variability between years. If that's ground level, we had 2 years here where it practically didn't come above ground level, and a whole string of years in the middle 90s where it never even got close. So the birds and the fish have to find a way of coping with this somehow. And we believe that this has strong relationship to the dynamics of the birds. So seasonal drying, drought, and flood events are really a natural part of the Everglades. We can exacerbate it a lot through water management, but these are natural features. Okay, here's one punchline, which is the history of nesting in the Everglades. You can see that that's 1931, that's about 2000. So that gives you an idea of the time scale. These are, this is 100,000 breeding pairs, so 200,000 breeding birds. These are the conservative end of the estimates that were done at the time. Big decline, obviously, 80 to 90% decline of the birds nesting. But the thing that really leaps out at you from this graph is the variability back here. Many years there were no birds nesting or very, very few birds nesting. That natural variability in the hydrologic cycles in the Everglades really does translate into boom or bust for the birds. That variability, therefore, is something that we would really like to recreate if we're going to restore the Everglades. We don't want it looking like a wading bird farm. We want it looking like it did. So that variability is very important to understand. We have variability here, but I think a lot of that, people would say a lot of that has to do with water management. Back here, we're pretty sure it did not. So what's all that variability about? How does that translate into nesting? And to talk about that, I'll talk about one example that I think we know about. And that has to do with these droughts. Here I've blown up the hydrograph a bit so that you can see that drought in the late 80s, early 90s. 2 years where 90% of the alligator holes went dry. It was really an enormous event. And the late John Ogden and I were sitting around on our thumbs during this period with no birds breeding, wondering what was going to happen when the water came back. And so we sort of took bets, and we both bet the same thing, and we said that here, after that first water cycle after the drought, we're going to have no nesting, none, because all these fish have died in here, right? And so, of course, you know, we bet the farm on that. The fish did die. We did have a fairly large nesting event during the dry down prior to that drought. And then we predicted that there would be no nesting. And of course, from the way I'm talking, you can tell that we had the largest nesting event in 40 years right there. When this happens, when scientists are wrong, really dead wrong, they've made a prediction and they're dead wrong about something this big, you know, some people say you should just cry. I say get out the champagne. You've just learned something really fundamental about the system. All the money that went into it is really starting to pay off because you've learned something really new and really, really important. And indeed, I think we did. So what's going on during these droughts? The first question is this was this just this drought cycle, or does this happen in other years? It does happen in other years. If you go back to that nesting record, you do find that all of the big, or nearly all of the big nesting events are preceded by a 1 to 2 year severe drought cycle. The big nestings and the droughts were defined here statistically. This wasn't us waving our magic wand. And in fact, the one big nesting that didn't quite qualify was also preceded by a drought. So we were fairly confident in this prediction. So what is happening during these droughts? We're having obviously no water on the marsh surface. We're having burning going on from lightning fires and so forth. We know now that the birds are really limited by the sawgrass on the surface. They just can't get down into it to forage. So we've opened up a lot of areas to forage. When the water comes back, that area is still open. We're also reliberating a lot of nutrients that are tied up in the above ground part of the sawgrass, and in some cases in the peat and the roots if it's a deep burn. Remember, this is a wildly oligotrophic system, very, very nutrient poor, and a little bit of nutrients reliberated can go a long way. So when the water comes back, those nutrients are now on the marsh surface for algae and periphyton to absorb, and that's exactly what these small fishes feed on. So there's a pulse of secondary productivity going on. We think there may be something else going on as well, and that has to do with big fish and little fish. We don't get fish quite that large in the Everglades, but we do get gar, so it's representative. The little fish, when they get back onto the marsh surface, they don't have much of a population. The big fish don't either, but the little fish have this really fast generation time and can outbreed the big fish, their predators, very, very rapidly. After about a year or so, maybe the big fish are starting to catch up, but for a while they're released from that predation. And so you get a big bloom of these small fishes. And this is actually being borne out by some of the work of Joel Trexler, who's finding crayfishes and some of the small fishes really go nuts after these big droughts. So you get this pulsing of prey, pulsing of the birds that may in fact create year-class cohorts of birds that are very important for decades at a time. So what processes probably produce these great big nesting events? Certainly the annual drying that I've talked about, certainly these irregular disturbances, and it may not be limited just to droughts. There may be hurricane effects that we don't know about yet too. But pulsing is very important. It was a big system. The birds, if things were bad nesting on the coast, maybe they could move inland to where there was more water. They could always move up to the lake. There were a lot of different conditions in this place that's the size of New Jersey. It was a big playground for the birds. Finally, the estuarine conditions, the meeting of fresh and salt water, the world over, is known to be more productive than usually freshwater marshes nearby. And indeed, that's the case for the Everglades. In addition, And that's where all of the historic colonies, that's where all those stars are, that's where they were all located. In addition, the birds also get safe nesting. If you nest in the central Everglades on a tree island, it can dry out, you can be invaded by raccoons and things. That doesn't happen in the coastal zone, so you end up with a lot safer nesting as well. Okay, so we think that's the way the world worked, more or less. Then, of course, you've all seen this slide a million times. We've had a major redistribution of water, and one of the most important things is the drying out of this estuary down here. That's the most strongly affected part of the entire ecosystem, right where the birds had their fertile crescent. What does it do when you dry out the marsh? These are some data from Bill Loftus, who worked at Everglades National Park for most of his career. Beginning in the 1970s, he was studying densities of marsh fishes, small fishes, at one spot in the central shark slough. And you get lots of variation from month to month, as you might expect, and you get lots of boom and bust. But the interesting part was that he compared this with a site just east, just 2 miles east of there, right here. That site had been over-dried by the L67 extension canal, which kept it from wetting up. There's the data for that site. So when you dry the place out, even for fishes that are wetland adapted, you're really cutting production off at the knees, and you're really reducing the density of fishes. Availability of fishes is the product of density and how shallow the water is, right? So if you take away the production, you have to dry it out so much to get any kind of an equivalent availability that it almost never happens. What about the estuarine zone? Jerry Lorenz at National Audubon in the Keys has spent a long time studying this, and he finds that the production of these small fishes is way higher as you move down the salinity gradient towards land. So under the estuarine, practically fresh conditions, that's where you're getting the maximal production of these fishes. As you add salt, it goes away. And so the clear prediction is if we restore flow to the coastal system, we're going to get a lot more fish. And that's probably what the birds used to rely on there. Okay, how did the birds react to all of this messing with water and drying? Well, as you can expect, not very well. You've seen the big decline in numbers of birds. There was also this massive movement from these colonies here to these colonies here. So the birds that were left also just moved away from the coast, told us very clearly in the 60s and 70s that the coastal zone was messed up and was not something that was really going to be useful for them. That was a very, very strong signal, and it occurred about 20 years prior to fisheries telling us that that estuarine condition had also been really messed up. In addition, we saw a decline in the nesting success of storks that went hand in hand with the fact that storks were nesting later and later. That relationship goes something like this. Storks used to begin nesting in November, December. And in order to do so, they had to get food in the peripheral marshes that were shallow at that time in the Everglades. Some of those peripheral marshes are now Miami. Some of those peripheral marshes really never wet up during the current scenario. So instead, now the storks have to wait until January or February for that slough to get to the point where they can actually start to get food. So their problem is that they also have a 110-day nesting period. And if you begin in February, there's no way that you're going to be able to bring off that brood by the time the wet season starts. So the typical scenario now is for storks to begin nesting in February and sometimes as late as March, and then end up abandoning their young still on the nest in May and June. So that also tells us something's really severely broken here. A lot of this information has now gone into the Everglades trophic hypothesis, which has to do with birds but also has corollaries with alligators and fishes and other things. And I won't read you each one of these boxes, but it's a formal way of stating all of the relationships that I've talked about. the topography, the water depth, the relationship between water depth and fish production, the coastal zone, all feeding in to the population size of the birds. It's also been translated into essentially a restoration hypothesis. And that is that if you get rid of some of the flow, the barriers to flow, and if you make the timing of flows more natural, you're going to end up with more of the smaller fishes, you're going to end up with more availability, you're going to end up being buffered from this need to draw things down into the last inch in order to make things available. If you have a higher prey stock, you're going to be able to have deeper water. And that will be over a much larger area. And we, as I said with my military transport idea, if you add those fish, you are going to get a lot more bird nesting. Now, the crucial part about this to me is that this can all happen really quick. All that stuff that Steve was talking about earlier could turn the place into a wading bird haven really overnight. I mean, you're talking about a 2-month generation time for these fishes. The birds respond very rapidly. This could be also a really early warning that things are getting better if they do get better. So I just want to point that out. Okay, you've seen that. We have some very clear predictions about what the birds are going to do. More birds, movement back to the coastal zone, more of these supernormal nesting events, earlier nesting by storks and better success, and more tactile foragers like storks and ibises than great egrets. So our indicators are very clearly linked to ecological variables and ecological response, and we're ready to see what happens and see what predicts, if our predictions come true. Now, there's also, and I mentioned the numbers of birds. There's this prediction that we're going to have small but variable numbers of birds before restoration and large but variable numbers of birds after restoration. And that prediction we made back in, 1995 or so. And then we got, oops, sorry, hit the wrong button. Then we actually got it. We got this great big increase in the numbers of birds in the late 1990s and early 2000s. It was called the bump because it was a bump. 3 to 5 times the numbers of breeding birds. And a lot of people said, wow, this is great. And I said, ugh, because we hadn't restored anything yet. So why were they, responding like this? This really made no sense at all. So here's another ecological surprise coming down the pike. And I'm going to, although some of this was related to some good hydrological years in those late 90s, early 2000s, there were also some very bad years during that time. And it didn't explain all of that bump. I'm going to tell you right now what I think happened, and that is that during this period, these birds were exposed to a lot of mercury. During this period, they were released from that mercury. And I'll try and convince you that a lot of that bump is due to that phenomenon. Historically, from feather specimens in museums, we know that white ibises and virtually all the other wading birds had pretty low mercury in the Everglades. But sometime in the late 80s and early 90s, they began having lots of mercury. And this was, in some cases, larger than any other aquatic bird in the world. These were some pretty high variables. The rest of the system was also showing the same thing. Fish, alligators, even panthers and raccoons were showing very, very high mercury. As it turns out, the Everglades is a great place to take mercury, the element in an old-style thermometer, and make it into methylated mercury, which is really just adding a methyl group. The consequence of adding that methyl group is that it's 10 times more toxic and vastly more likely to bioaccumulate up the food chain. The methylation is occurring down here in the soil-water interface, and it's being done by bacteria, sulfur-reducing bacteria, which are anaerobic. So the Everglades turns out to be a fantastic place. We can methylate 100% of mercury in 24 hours. Nobody ever measured that before. So we're very, very proud of that. We also have very long food webs between water and a largemouth bass. There's a biomagnification factor of 1 to 3 million times. So we're great at turning mercury into its worst form and then concentrating it as much as possible. So we're number one. Okay, the mercury was coming, as it turns out, from Miami. It was coming from the urban zone. They don't have a lot of space for landfills in South Florida. A large percentage of the household trash is incinerated. Up until the early 1990s, most of the mercury coming out of those smokestacks was coming from small household batteries. Beginning in the, I didn't know that. Beginning in the early and mid-90s, the battery companies figured out a cheaper way to make batteries without the mercury. So overnight, the industry changed. So this created, as it turns out, a very interesting experiment. What happens when you turn off the mercury? So 75% was coming from these incinerators, and 75% of the mercury coming from the incinerators was from the batteries. That gives you an idea of the magnitude. In addition, we also knew that the sulfur-reducing bacteria that were doing the methylating need sulfur. They were getting sulfur in the form of sulfate from the agriculture industry, it was coming through the water into the central Everglades. That has since been grossly reduced as well. So two potential sources for reducing mercury or its effect. This is a retrospective of the magnitude of that reduction. Here's 1990, here's World War II. We now have levels of mercury pollution going into the Everglades that are less than at any time before World War II, since World War II. That's a pretty major statement and a pretty major experiment for somebody who studies contaminants to find. We also know, as I've shown, that we had the bump at about the same time that we had the decrease in mercury. Are the two related? I don't know. It might have been Japanese politics that somehow produced this bump. It seems like it might have been, but as I say, there's a lot of other variables, and correlation is not causation. So in order to try and get at some of that causation, like an idiot, I took 180 white ibises into captivity and began dosing them with mercury at levels that they would have gotten in the early 1990s in the Everglades to see if the effects really were as bad as we thought they might be in terms of reproduction. Answer, they were. We had some unexpected things go on. Number one, we had a lot of birds that weren't laying eggs. And because the birds had been sexed genetically, we knew that there were a lot of male-male pairs in the dosed groups. And there were more male-male pairs, the more the dose rate. So there was a very clear relationship there. This turns out to be because their endocrine system was really compromised, and as it turns out, mercury does do this in fishes and other animals as well. Just in case you think I've found the mother lode of information about homosexuality in humans, forget it. It's a totally different situation in humans. It's not even some of the same hormones. And in fact, in this case, it was courtship that was messed up in the birds, and that's why no females would pair with them. Just to ease your mind, there are lots of places in the world that are hotspots of mercury that have high human consumption that have been studied intensively. And no, we don't have hotspots of human homosexuality there. So get that off the table. In addition, we also saw that the heterosexual pairs that had mercury also were just crummy parents. They would walk up to their young, they would feed them, they would look at them, and then they would beat them up. They would push their own eggs out of the nest. They would neglect their eggs and chicks in full sunlight where they should have been shading them. They were crummy parents. When you add up these two effects, you get over 50% reduction in reproduction. If that happened to the human population, we would all die off pretty quick, wouldn't we? So that's a really big effect, something that was mediated by this one toxin. Okay. I'm going to start wrapping up with the sort of litany of surprises that these birds have shown us. First, they showed that the estuary was collapsing. They did it before a time that any of the fishermen or commercial fisheries had really noticed that something was wrong. They moved. That's how they told us. There was a change in population that very clearly indicated that something was wrong with their food. And that we now know was this problem of overdrainage and reduction in the prey animal population and their availability. Their reproduction also clearly signaled later on both the exposure to a major contaminant and the recovery from that contaminant, both of which were surprises. When we first started finding high levels of mercury in the Everglades, everybody was going, what? Where is the source? It wasn't clear that this should happen at all. And then when it was reduced, everybody said, wait, this is happening too fast. But the birds were very clearly indicating what was going on. They've also shown us through the drought work that wetland dynamism is crucial, not only to the functioning of the birds and their ecological attributes, but also probably to lots of other things. It's what makes the Everglades the Everglades. It's why the Everglades is dominated by small fish, not large fish. It is clearly a process that we want to keep. And the combination of bird studies and fish studies and hydrological modeling that Steve referred to earlier has all kind of converged on roughly the same historical hydrological pattern. How much water do we need? It all pretty much says the same thing. So this has been an enormously successful monitoring program. I want you to consider for just a minute what would have happened if we had started our surveys here instead of way back here. So first off, we wouldn't have known about this big decline. Second off, we wouldn't have known that this kind of variability was at least in part generated by natural processes. We would probably not have known that the birds were naturally not contaminated back here. It really would have been a totally different story. We also would have suspected that the carrying capacity of the marsh was at this level, and that in fact, we would have believed the story. Oh, it's a oligotrophic system. It can't support very many birds. Oh, that makes sense. And so we would have gone along thinking, oh, let's just manage at this level. So the power of long-term monitoring is really enormous. I feel very, very lucky to have been able to work with that past data as well as the present data and really be able to interpret. I also just want to give you a flavor of where we are now. We're now at the point where we can put these models together of water, fish responses, bird responses, and really start looking at, as Steve was talking about earlier, some of these scenarios for how we're going to make the best use of the water that we're going to get out of SEP. And this is an example with wood storks. This is done by James Behrens and Eric Noonberg at Florida Atlantic. And their modeling suggests that in this red stuff here and here, the very deepest red is a 100% increase in the numbers of wood storks foraging in those areas. That gives you some kind of sense of how important this is and how fine we're getting in our ability to predict what's actually going to happen when we start turning the taps. So science, once again, is important. My hats are also off to the Audubon Society wardens who began all this, who in some cases risked their lives and certainly gave a lot of blood in the form of mosquitoes to defending these things and also to counting the birds. Keep in mind, they were counting the birds because they were supposed to be defending the colonies. It was something to do. And they never dreamed that we were going to get this kind of data and this long-term data set out of it. So my hat's off to them. I wish everybody had a data set that was that long. There are enormous uncertainties ahead, as Steve alluded to. Mercury is not the only thing that can contaminate the Everglades. There are lots and lots of other things, and we are creating novel contaminants every day. Every year there are lots of new things on the market. There's also the question of distant magnets. And here I mean what happens when Louisiana crawfish aquaculture starts back up because the markets are good and they draw off 50% of Florida's birds. That actually has happened before. So distant magnets are, we could restore the Everglades perfectly and not get the response that we think we will. Rising sea level is a big one. To me, it's not that big because I actually think that whether the estuary is here or here is kind of irrelevant to the birds. We're going to have the same ecosystem functions in a restored Everglades. We just need the fresh water. The cities are thirsty. There's really great concern about this, that they may grow. Both agriculture and the cities are, always wanting more water. A 10% decrease in either the amount of rainfall or the amount of water that we get allocated, Everglades restoration essentially won't work. So we have to be really watching that barn very carefully. Phosphorus pollution, I think Steve talked about that. I think the biggest one is political will. Trying to make sure that, we're at the crest of the hill. We're about to hit the downhill in Everglades restoration. And yet now we're stuck with Congress that wants to do nothing and spend nothing, and that really has no patience at all for ecological restoration as a priority. That's something we've got to help get them over. Okay, I'm going to stop there and ask for questions. Thank you very much.